Jason, I don't know if you can see, but we have about 30 to 50 people in the room, as well as those on Zoom. So a big crowd for you today. For those that don't know, Jason is a new member of the ChatGPT team at OpenAI, if I'm not mistaken. And formerly, he was a senior research scientist at Google Brain, where he worked on emergent abilities for large language models, Flan instruction tuning, and chain of thought. And so without further ado, take it away.
Yeah, thanks, Shane and everyone for the introduction, and thanks for having me here. Today, I'm just going to talk about some intuitions about large language models, basically covering what their abilities are and sort of how we can make them more usable. This is a quick outline of the talk. So it's sort of split into four short sections. The first section is going to be going over the intuitions of what language models can learn from predicting the next word. The second part will sort of discuss why language models have taken off recently and not 10 or 20 years ago. The third reason, or the third part is going to talk about how we can get language models to do more complicated tasks. And then finally, I'll talk a bit about how language models can be made to be more user-friendly. And if there are any questions during the middle, feel free to interrupt me. I think there'll also be a QA at the end. Great, so as a review, language models are basically like a super good next word predictor. And it's sort of good to think about exactly what this means. So here's an input of what the language model might get, and then what the language model actually outputs. So the input is like some arbitrary sequence of words, like Dartmouth students like to. And then what the language model outputs is, in the most basic form. This is not ChatGPT, but what the language model outputs is basically like for each word in the dictionary, it outputs the probability of that word being the next word. So here's basically all the words in the dictionary on the right. And then, the probability of the next word being A is super low. And then aardvark is also super low. And then, some words have higher probability, like drink or study. And then all the way to zucchini. And these are just hypothetical probabilities. And basically, what language models do is they take in like these big training corpora, which are basically texts that are crawled from the internet. And then they're optimized to predict the probability of the next word. And what it sort of learns from this process is that if you see certain words, wait, you can't hear me?
I think we can hear you here. I don't know what, yeah, exactly.
Shane, you're also muted, I think. Oh. Okay, I guess we can wait for the room to reconnect.
Hey, Jason. Sorry, we disconnected. Could you restart from right after zucchini?
Yeah. So
Thank you.
You can hear me now, right? Okay, good.
Yes.
So yeah, basically what the language model does is it outputs the probability of like every word in the dictionary. And this is just the numbers on the right are hypothetical. And this is, yeah, basically the language model's prediction of what the next word might be. And the way that language model training works is that basically the language model takes in like a huge training corpus, which is text crawled from the internet. And then it's optimized to predict the probability of the next word. And what it sort of learns from this process is that certain words in the input, if they're seen, might be correlated with higher probabilities of certain words in the output. And then for this unseen piece of text, you basically get the probabilities like the ones shown here. And then the way you actually pick like which next word to produce there are various ways of doing that. But I think the simplest one is that you can just pick the highest probability one and say that's the next word you're going to predict. Is that clear? Let me know if there's any questions with this. Okay, so I'll go over a couple of examples of like what language models can actually learn from this next word prediction task. So a first very easy thing that language models can learn is sort of grammar. So take this example. In my free time, I like to. And then the language model learns that the next word is probably not a noun, and it's probably a verb. And again, these are just hypothetical probabilities. So it learns something about grammar just from this next word prediction task. Language models can learn facts about the world. So here's an example of an input. The capital of Denmark is. And then maybe the language model saw this on the internet somewhere. And then now it kind of knows that the next word probably is Copenhagen and not London. And this is also pretty easy. You can learn this just by figuring out, oh, if Denmark is in one of the input words, then probably you should upweigh the probability of Copenhagen being the next word. Language models can also learn things like lexical semantics, or learn about like what the identity of words are. So if there's a sentence like, I went to the zoo to see giraffes, lions, and, then the next word is probably going to be upweighed to be something like zebras. So it's probably something related to giraffes and lions. Here's another example. They can learn even more complex things like sentiment analysis. You have an example here of, I was engaged on the edge of my seat the whole time. The movie was. And then the language model sort of has to understand what the previous sentence meant, and then it can decide whether it wants to upweigh like good or bad. And then maybe it's looking at some correlations here where, okay, if I see engaged in the past sentence, then maybe that's indicative of positive sentiment. And it doesn't have to be like a super surface level form thing, and it can actually even require more complex understanding. So here the input is like, overall, the value I got from 2 hours of watching it was the sum total of the popcorn and the drink. The movie was. And then here, some more complex understanding is needed for the language model to do this task. So it has to, there aren't that many surface level correlations it can rely on, and maybe it has to really understand what the meaning of the sentence is if the person said the sum total was the popcorn and the drink. Sorry? Okay. And then language models can even learn things like translation. So here's like a super simple example where maybe somewhere in the training set, the language model read the sentence, the word for pretty in Spanish is, and then it learns to upweigh the probability of bonita. And if there's multiple languages in the training set, then it can actually get a pretty good understanding of languages that are also not in English. And then maybe it can also even teach language models to do things like spatial reasoning. So for example, you might have some sense in the training set like this. Iroh went into the kitchen to make some tea. Standing next to Iroh, Zuko pondered his destiny. Zuko left the blank. And then, maybe the next word, the language model learns that, okay, if Zuko was standing next to Iroh and Iroh was in the kitchen, then the probability of the next word being kitchen is probably high. Okay, I'm just making sure I didn't lose everyone. Okay. And then finally, here's another example where the language model can probably learn to do like even easy arithmetic tasks. So something like 3 plus 8 plus 4. Maybe it's seen that exact example in the massive training set, or there's enough examples that are sort of close enough that it could probably figure out that it should be 15. I also wanted to give some examples of things that language models can't do just by doing next word prediction. So here's one example. If the input is the stock price of Apple on March 1st, 2023 is, the language model was probably trained before today, if you're using it today. And so it probably can't figure out that world knowledge just by being trained on text from the past. Here's another example. So if you have like an arbitrarily long arithmetic question here, like this, multi-digit arithmetic operation, the language model probably can't figure out how to do that. The reason is basically there's not enough like similar training data on the internet of like these types of questions. And also, if there was, it's pretty hard to figure out what the pattern is to get the output. And then also language models probably can't do math questions that you probably wouldn't be able to do. And this is, we're making progress on it, but I think this is still generally true. So if you have a math problem like take the 19th digit of pi and multiply it by e to the 4th power, the resulting ones digit of the resulting number is. And I guess the reason language models can't do this is there are a lot of intermediate steps that are sort of going on here in order to get to the final answer. And it's like really hard to figure out the pattern of how to do problems like this just by looking at predicting the next word in the training corpus. Language models also are probably bad at predicting the future. So an example is like the winner of the FIFA World Cup in 2026 is, and then I guess like, it's natural that the language model will be bad at this. I don't think anyone can do this super well. Also, language models are bad at information that isn't in the training data. So for example, if you say Jason Wade's favorite color is, I don't think the language model will be able to figure this out. Just because like, something that's not seen in the trained data, the language model is just gonna have to guess or make something up. And then a final, I think, open challenge for language models is that they can't really take in extremely long pieces of text. So for example, if you like try to shove in an entire 2,000-page Harry Potter fan fiction, and then you ask it about a certain part, like what happened after Harry opened the chest for the second time, the language model isn't going to be able to process that huge piece of text. The sort of current state of things is that we can't really take in very long inputs, like we're limited to around 4K words. Okay, great. So I guess the sort of rule of thumb that I'm proposing here is that language models can do, like with decent accuracy, most things that an average human can do in 1 minute, I guess, without the aid of searching up the internet. And I guess one way that you can sort of look at this, and we'll go into this in more detail, is like maybe today language models can do like a bunch of things like simple math, common sense reasoning. They have world knowledge, they can do translation, they can do sentiment analysis, they can generate coherent text, they can be grammatically correct. But there's also a lot of things that they can't do, like abstract reasoning, high-level planning, playing chess well, making clinical diagnoses, or protein discovery. But this is a pretty big difference from what sort of the state of language model was in 2018. I think in 2018, at best, we were able to do like a few things with language models, and they definitely weren't as compelling as they are today. And then what sort of excites me is that if you sort of extrapolate this trend where just 5 years ago, language models were so much weaker, I'm excited about the capabilities that language models will be able to have just a few years into the future. So moving to the second part of the talk, which is going to be about why language models have gained this new ability. This is basically going to summarize a paper that was published last year called Emergent Abilities of Large Language Models. And just to have some sort of background for emergence, basically for several years now, we've had this observed relationship in language models where, on these plots, the x-axis is basically like how much compute you're using to train the language model. And then the y-axis is like the test loss. So like lower is better on this. And basically, what we have observed is that if you increase like the amount of compute used to train the language model, the size of the data set trained to use to train the language model, and the parameters, which is like the size of the language model, you can get this like reliable improvement in like how good the language model is. And the reason this is important is that it's reasonable to expect if you continue increasing compute and training data set size, the language model will get even better. And while that sort of improvement is predictable, there's these tasks that performance does not seem to continuously improve as a function of scale. And the interesting thing is you can't really predict these tasks ahead of time. So to zoom out, emergence is sort of this phenomenon that's been seen throughout science. It's probably first popularized in 1972 by Philip Anderson, who was a Nobel Prize winning physicist. Here's this blog post from Jacob Steindar, who's a professor at UC Berkeley, and he gives this following definition of emergence that I liked, which is emergence is a qualitative change that arises from quantitative changes. And some examples of emergence in science include like, uranium. So with a bit of uranium, nothing happens. With a large amount of uranium packed densely enough, you get a nuclear reaction. Or for DNA, given only small molecules such as calcium, you can't meaningfully encode useful information, whereas given larger molecules such as DNA, you can encode a genome. In this paper, we basically had this definition where an emergent ability of a language model is basically defined as like an ability is emergent if it is not present in smaller models, but it is present in larger models. There's sort of this natural question of like, how do you define like what's a small model and what's a large model? The main way that we're going to focus on, and I think there's two pretty decent ways, is training flops, which is basically the number of floating point operations that's used to train the language model. And then also you can look at it in terms of the size of the language model, or like the amount of compute needed to like inference one example. But you get similar looking plots from both of those. So the first type of emergence I'm going to talk about is emergence in the few shot prompted setting. So this is very similar to the basically next word prediction setting that we were looking at before. And the only difference here is that you typically give like one or more examples of the task as part of the input. So you want to get the sentiment for the review, I love this movie, and the output is positive, and to sort of let the language model know like what's the task you want it to do. You can append like an input before that. So for example, this movie sucks. And the sentiment is negative. The sort of definition that we use for emergence in this setting is a few shot prompted task is emergent if it achieves random accuracy for small models and above random accuracy for large models. So here's sort of 8 examples of emergent abilities in the few shot prompted setting, basically across a range of different language models. So the way that you read this graph is that each of these 8 plots is like a different NLP task. And the x-axis is model scale. So as you move to the right, you're putting more compute into your language model. And then the y-axis is like how well you're doing like a certain task. Basically, and we've also plotted like a bunch of language models from Google, DeepMind, and OpenAI. And the sort of pink dotted line is the baseline of random performance. what you basically see in these plots is that the performance of language models is about random for like a bunch of small model sizes. And then suddenly when you scale to like a large enough language model, the accuracy will spike to well above random. And the point here is that if you sort of only looked at the small language models, you might guess that, if I kept scaling up, it would still be random. But in fact, it's actually the opposite, where you scale up and then at some threshold, you see this emergent performance where the model suddenly is able to do the task. To be a bit more concrete about like what these types of emergent tasks are, here's a few examples. So there's this one task called multitask NLU, or also MMLU. And basically it's like a compilation of like high school through professional exams. And here are a couple of examples. So there's like a microeconomics example. One of the regulations that government discourages and regulates monopolies is that. And then it gives 4 options, and the model has to output A, B, C, or D. And basically, it's taking a test. And there's also, example with college mathematics. So, in the complex Z plane, the set of points satisfying the equation Z squared equals absolute value of Z squared is A. And then there's 4 options the model has to pick. Basically what we can see is if you look at the plot on the right, for the three small points, you can see that basically small models are doing random on this task. So they're not any better than just guessing on these exams. But once you scale up the model, so for example, Google's Palm model or DeepMind's Gopher and Chinchilla models, then you see that the accuracy on this actually starts to get very much above random. And again, you wouldn't be able to predict this emergent performance just by looking at the 3 smaller model points. Here's another example from a benchmark called Big Bench. And basically the task is the language model has to take in like an arbitrary input sentence, like the 1931 Malay census was an alarm bell. And then it has to give the IPA, or like International Phonetic Alphabet transliteration of that sentence. And then here, the performance is measured in like this, it's called BLUE. And basically it's like an n-gram matching metric where you like match which sets of words that are in the ground truth are in what the language model generated. So it awards some partial credit. And what you again see is that when you pass this sort of threshold of like 10 to the 22 training flops, then you get this performance that's well above random on this task. Another interesting result that I want to talk about is from this separate technical report that I put out recently. And basically, there's this interesting question of like, are there some tasks where if you increase the size of the language model, the performance actually gets worse with scale? So here's an example of one task that they found. So basically, it's called quote repetition. And what the task is that the input is something like, repeat my sentences back to me. All that glisters is not glib. All that glisters is not. And then the language model has to successfully output glib. And what sort of happens when you give the language model these types of outputs is if the language model is small, then it's like not super capable and it just is able to copy the word glib. And so it actually gets like 100% on this task. The second point here is like if you use like a medium-sized language model, the medium-sized language model actually knows the word, like the phrase, all that glisters is not gold. So it actually does worse than the small model because it sort of has this bias towards outputting like an actual quote. And then you might expect that, oh, if you like scale a large model, it's going to do even worse. But we find that the large language model, if you keep increasing the scale of the model, is going to actually do better. And the reason is the large language model also knows the quote. All that glisters is not glib. But it also knows how to interpret the instructions, read my sentences back to me. So it's able to avoid saying all that glisters is not gold and successfully do the task with 100% accuracy. And the point here basically is there are some tasks where, yeah, the model performance may actually get worse as you increase the scale, but it could actually go back up again if you keep on increasing the scale past that. And here's sort of the hand wavy diagram that I like to show for this. So you can imagine, like, on the x-axis is the scale of the language model. So, you know, as you move to the right, you're looking at larger language models, trying out more compute and more data. And this sort of imaginary y-axis is like the spectrum of things that language models can do. And the blue shaded area sort of represents like what language models can do. And basically what the sort of cartoon is trying to show is that as you scale up the size of the language model, it can do like a larger range of tasks. And emergent abilities are, like, say, you know, at some threshold, are these new abilities that large language models can do, but small language models can't do. Okay, so on to sort of the third part of the talk. Basically, we've been looking at this sort of prompting technique where you add an example into the input, and then you want the model to, like, perform some unseen, perform the same task on some unseen example. So on sort of the left diagram there, we have standard prompting, where basically you're doing just that. So for example, you have a math question and an answer, and then you give the model an unseen math question, and it sort of has to perform that task. And unfortunately, it gets it wrong. So the thing that we proposed in chain of thought prompting is that instead of just giving the question and the answer, we want to also teach the model how the task is performed. So we sort of add this sentence highlighted in blue. Roger started with 5 balls, 2 cans of 3 tennis balls is 6 tennis balls. 5 plus 6 is 11. And this intermediate reasoning step basically activates in the model, oh, before I give the final answer, I should give some intermediate reasoning steps that might help me get to the answer better. And then when we insert that change, it actually enables the language model to do a lot better on these types of tasks. So I can do like a quick demo, just using the GPT-3 API. So let me know if I'm not sharing a different screen now. So basically, here's how you might traditionally do it. Great. So, you know, you have like a question, a math question, and then an answer, and then a math question, and then the answer, and then a math question, and the answer. And then let me delete this. And then you have another math question, and language model is expected to answer. And unfortunately, it looks like it's broken, but the point is, unfortunately, it would not work. Okay, I'm not sure why it's not working. So yeah, maybe I only have the free account. But okay, so basically what's going to happen is the language model is not going to be able to do this task. But when you make this simple change of adding in like reasoning steps in the exemplars, so, you know, in the few examples that you give the language model, if you add these like intermediate reasoning steps before the language model gives the final answer, let me try again. Maybe it doesn't work. Okay. Basically, the language model will be able to produce the reasoning before it gives the final answer. I'll go back to my slides. Okay. So here, I guess here's one example. So basically, if you can see on the right, you know, if you prepend examples of reasoning in the exemplars that are given to the model, for this new question, can you hide a basketball in a sandcat's ear? The language model is able to give reasoning. So it says like a basketball is about 30 centimeters in diameter, a sandcat's ear is about 2 centimeters in diameter. Thus, a basketball would not fit in a sandcat's ear, so the answer is no. And then one of the interesting things is you can sort of plot the performance of like different size language models and whether they're able to have this chain of thought reasoning ability. So on the x-axis here, we have like the scale of the language model. So basically you can look at the size of the language model and we have 3 points. And then you can have both standard prompting where you don't give the model reasoning pads in the examples, or you have chain of thought reasoning where the language model is like prompted to give reasoning before it gives the final answer. And you can see there's like a huge difference in performance when you use chain of thought. And often you can beat fine-tuned state-of-the-art, which is like the task-specific model that does the best before this, just by using chain of thought prompting. I'll show another like large-scale empirical result here. We basically had this benchmark of like pretty challenging problems where like no model had beaten the average human rater before this. So here's an example of a problem. Maybe let's pick this one. So, the question would be something like, if you follow these instructions, do you return to the starting point? Turn left, turn right, take 5 steps, take 4 steps, turn around, take 9 steps. And then the language model has to say yes or no. And basically, this is a really hard task if the language model only has to directly say yes or no. But if you prompt the language model to do reasoning, then it can actually like keep track of state and do this like pretty complex problem and get the final answer correct. So say something like, oh, we start the origin 0, 0 facing the positive y-axis. And then if you turn left, you're facing this side. If you turn right, and then it keeps track of which point you are. And then at the end, it reasons and said, okay, are we at where we started? Yes. Here's another example of like word sorting. So this is like actually a pretty challenging task for language models because it doesn't really know like it's never told explicitly what the characters and the words are. It's just like words are just given to the language model as IDs. And the interesting thing here is you can also get the language model to sort of sort the individual pieces of the list one by one, and then finally give the final answer. And here's sort of a summary of the results from this paper. So basically, we have 2 columns. One is the performance on like the average of the 23 tasks in this benchmark called BBH. And then the other column is a number of tasks where the language model is performing above the average human rater. So you can see like in the prior work, no model was beating these average human raters. And then when you use chain of thought prompting, you get this massive gain where like on 17 out of 23 of the tasks, you get this improved performance. And this little graphic on the bottom is just like, you can look at the delta with respect to the language models and average human raters on these 23 tasks. And then if you do the standard sort of prompting without chain of thought, then you get worse performance than the average human rater on most tasks, as shown in the red bars. And then when you use chain of thought prompting, you actually can get above human performance on like most of the tasks. And here is, let me see if I missed something in the chat. Okay, and here's another example of chain of thought being an emergent ability. So basically here are like 3 language models. And then the y-axis is like the scale of the language model. So as you go right, the language models get bigger. And then that's the x-axis. And then the y-axis is the like average performance on this benchmark. And basically what we see is that for like small language models, chain of thought either doesn't work or actually hurts performance because the small language models don't really have the ability to reason. And then as you increase the model size, the chain of thought plot, which is the blue, is actually above the baseline, which is black. And what that shows is that it's sort of this emergent ability where once you pass a sufficient model scale, then you get this positive delta from getting the model to reason about the problem. I realize I'm running short on time, so I'm gonna skip the rest of these slides. I'll talk about this one. So um, the way that I sort of think about chain of thought prompting is that we have like a similar cartoon to the one I showed previously, where the x-axis is the scale of the language model and the y-axis is the spectrum of NLP tasks. So with standard prompting, you see like, yeah, you can increase the range of tasks that the language model can perform. But with chain of thought prompting, at a given model size that's large enough, you can actually like strictly increase the number of tasks that the language model is able to perform just by prompting it in a different way to do those tasks. Yeah, good question. The question is, can chain of thought like reasoning be taught to smaller models? The answer is yes, if you fine tune it, but there's a lot of challenges. Like it's tough to sort of collect that data for small language models. But I think the interesting thing is that as we get better at training language models, we'll have smaller models, say 2 years from now, that were maybe much better than like the best big model that we had in like 2020. Yeah, this slide basically shows that there's like a little hack that you can do with chain of thought prompting, where basically you get the language model to like give different reasoning paths, and then you take the majority vote over the final answer. And this has like a surprisingly large performance gain. And then another interesting result here is that like you can get the language model to actually do chain of thought reasoning in like a bunch of different languages. So the language here is Bengali, and Bengali is, I think, like the 6th most spoken language in the world, but like actually on the internet, it occupies a very small amount of like the training corpora used to train the language model. And basically what you can see is that you can even get the language model to do like math word problems in Bengali. So here's sort of an interesting plot where the x-axis here is like the frequency of the language in the pre-trained data set as a percentage of like the words in the pre-trained data set. So English is like 80% of the training data, and then you have these sort of like unrepresented languages like Swahili or Bengali, which are like 0.01% of the data set. And then you can measure the language model's ability to do like the same math word problem in different languages. And the interesting thing is that like you actually get the surprisingly high performance, even for languages that the language model hasn't seen much in the training data. So for example, like in Bengali, it's getting like 45%. And the reason this is interesting is that like the language model probably hasn't been trained on Bengali math word problems, but it probably has been trained on some Bengali, and it's been trained on some math word problems in English. And what's able to do is sort of generalize both those skills together to do math word problems and Bengali. Yeah, and I think I'll talk about this briefly, limitation of chain of thought is basically that if you do this chain of thought prompting, it's pretty task specific. So you have to write the examples in order to get the language model to do well on the new unseen example. And I think one of the important implications of this was like chain of thought prompting like really unlocked the ability for language models to do like a much larger range of tasks, like for example, math word problems. And given this like explosion of new tasks that are sort of solvable by language models, I think we should be pretty open-minded about what tasks will be solved in the next even 1 or 2 years. Okay, and then the final part, which I will try to cover in like 5 minutes, is basically how do we make language models more user-friendly? So far we've sort of been just talking about language models as next word predictors. What that means is like if you give the language model an input called like write me a poem about bananas, it's sort of trying to predict the next word, right? And it doesn't know that this is the end of a user input and I'm supposed to actually respond to it instead of just putting the next word. So if you use a language model that's just simply pre-trained, then it might say and other fruits, make sure the poem rhymes. So it doesn't know that, oh, that's a user instruction and I'm supposed to reply. And the behavior that we sort of desire here is that we want the language model to know if the input is write me a poem about bananas, then the user actually wants the language model to write the poem and not to just complete the next word. There's basically been this paradigm called instruction fine-tuning. This is the paper that's from, but maybe I'll show this slide. So there's a bunch of different instruction fine-tuned language models, but I think this sort of diagram captures it well. So the way that it works is basically you can take a bunch of tasks and append human instructions of what the task is to those tasks. So for summarization, you have like instruction that says like, how would you rephrase that in a few words? And then for sentiment analysis, you can say like, on a scale of 1 to 5, I would give this A. And then for question answering, you can just like simply ask the question. And then basically we're like training the language model on like a bunch of these examples of instructions for tasks. And then what happens is the language model can actually perform like unseen tasks just phrased as instructions. And the cool thing is you can just basically say what you want, and the language model will do it instead of having to phrase it as the sort of next word completion task that we've been looking at before. I think the interesting thing that we proposed in this work is that if you increase the amount of tasks, for like the tasks being like summarization, sentiment analysis, question answering, if you increase the number of tasks that you sort of do this instruction fine-tuning on, then you get a lot better model performance. And also you get the performance if you use larger language models. So the way that we sort of did this is that we basically took all the tasks that we could find from prior work and we merged them into one mixture and did fine-tuning on that. And we also wanted to unlock the ability for language models to do chain of thought reasoning. And so we included these data sets where we had these chain of thought annotations as part of fine-tuning. We basically did an evaluation on like tasks that were not included as part of fine-tuning to measure the generalization of the language model on any arbitrary task that you might want to evaluate on. And we also did this sort of paradigm where we trained on both examples with and without like these few shot exemplars. So for example, you might have just an instruction without any exemplars. Or you could have an instruction with exemplars where you like prepend an example of a question and an answer before giving the inference example. And yeah, we can also add in chain of thought as part of the target in both the zero shot and the few shot setting. And we basically propose like a whole suite of models here. The Flan T5 models are actually ones that are open source, so like anyone can download them and use them. Yeah. Oh, and the other interesting thing is that like this process of like fine-tuning the language model to follow instructions is like pretty compute efficient relative to like how much compute we're using to pre-train language model. So like it's only like less than 1% of like how much compute you're using to do the language model pre-training. And then these two plots basically show that as you increase the scale of the language model, the performance will also increase. The plot on the right shows that if you fine tune on like more data, then the performance will also continue to increase. Yeah, and then this slide basically summarizes that we achieved a new state of the art on several benchmarks. And then finally, I'll just show this example on the right. So basically what this shows is that like you can get the language model to do reasoning in a zero shot setting, basically without any examples of reasoning. So if you take a model input, like which statement is sarcastic, and then you look at the option, there are like two options. And then you ask the model, let's think step by step, and the model tries to complete that. If you take a model without instruction fine-tuning, it might say something like, what is the speaker trying to say? The speaker is trying to say that he has never had a takeout meal. that has used plastic containers before. And so it's like, it doesn't really know like how to actually do the reasoning. And it sort of rambles on. But for models that have been instruction fine-tuned, so the green one here, it's able to just directly say, okay, the reasoning is that plastic containers are very common for takeout meals, so the answer is B. And then we also had this nice usability evaluation where we compared like whether human raters preferred outputs from instruction fine-tune versus non-instruction fine-tune models. And basically across every scenario, the instruction fine-tune model was preferred. Yeah. And then here's sort of an example of like what the difference is. So if you give the model an input, like make a word that means when two AI users go on a date, on the left with the Palm 540B output, you know, it sort of repeats itself and then starts talking about other text, which is coherent, but it's not really the answer that you want. And then on the right, it sort of directly knows what you want and gives you the answer. Yeah, and then here's just a result talking about the public checkpoints that we released, getting good performance with respect to the amount of compute that they've been trained on. Yeah, so I guess the takeaways here are that when you're doing this instruction fine-tuning, it's better to train larger language models and to train them on more data. And then also it improves zero-shot reasoning and the usability of the model by a large margin. Great. So I guess to conclude, the sort of main point I wanted to make is that language models get these sort of new abilities as they get scaled up. And one of these really, I think, crucial abilities is the ability to do multi-step reasoning, which unlocks like the ability for language models to do like these complex new tasks. And because of these trends, I think it's reasonable to believe that language models will continue to get bigger and better, and we'll see new abilities that may emerge. Great, yeah, and these are just some examples of like personal interests that I think are exciting to explore moving forward. Yeah, thanks for listening. I guess one last thing I forgot to mention is that there are like multiple ways of doing instruction fine-tuning. You might have seen like RLHF being one of the ways. And I think, yeah, RLHF is kind of the way behind GPT. It wasn't the way that was super popular before that. But I think, yeah, there are a lot of valid ways, and it's hard to sort of compare them apples to apples. But yeah, so I think, yeah, basically the results I presented about Flan are just a small piece of what you can do to get the language model to follow instructions better. And happy to answer questions about that also. So I guess I should end the slides here and take questions if there are any.
Thanks, Jason. Amazing talk. We curated a list of questions that the instructors voted on. They're pre-submitted by the students. But before that, I want to see if there's any burning questions in the room in response to the talk. Maybe the first question then, Jason, Carolina, is she here? She had a question about the future applications. Oh, you want to ask that? I do, okay.
If you come up, you can use the mic.
Sure, she'll come up and ask it.
Carolina?
So there are a lot of questions about the future capabilities of these models. And so which ones are you most excited about, Jason, that you think will be most relevant and useful in the future?
I think, you know, as the sort of chain of thought line of work alluded to, the ability for language models to solve like challenging tasks requiring reasoning is really exciting to me. Like there's a paper that showed that like on these sort of college level exams, like this was like a math test that I'd probably get like 10% on. Language models could do like 50%. This is called the Minerva paper. And I think results like that are just super inspiring because it was something that I did not expect would be able to be achievable. Uh, uh, in the next few years, and it was achieved very quickly after I had that thought. So I think, yeah, and I guess, if you go back to sort of the history of AI, there were like people saying like 2018, language models will never be able to do reasoning or something like that. And I think it's so, it's just like really exciting to see like these tasks being solved very quickly and for them to be, for language models to do them well and sort of demonstrate this reasoning-like ability that's actually pretty strong.
Awesome, thank you. Julian had a question about the role of larger versus smaller models. Is he here? Do you want to ask that?
Yeah, basically the question is like, what do you think is essentially the goal to, because it seems like these results show that like if we just keep scaling things up, we're going to get better and better results. Is the goal just to keep making these models like bigger and bigger and bigger, or like is there still fruitful work in trying to like make these models smaller? Because to some degree, for some problems, we'd like to think that like the representations for certain concepts don't need to be overly complicated. I don't know, like what do you think? And also right now, like what do you think the role of smaller language models can be?
Yeah, that's a great question. So I think there's sort of this competing paradigm where if you know what task you want the language model to do, and you have a lot of data for that, then actually you don't need the language model to be like super large. I guess the sort of benefits of scaling up the language model is that a single model can do like a large range of tasks that are not specified at training time. I can just give like a concrete scenario. So like if you just want to do like translation between like two languages, you probably have a lot of training data that does that, and you actually don't really need like that many parameters to do the translation. So in those examples, you want to keep the cost of the model down. So it's probably better to just fine tune and not scale up the language model a whole bunch. So I think there's definitely a lot of work that's interesting and can be done to like enable like task-specific models to be productionized and used in the world. And also, I guess a general point is that although scaling has been shown to like improve performance a lot, there are also other ways to improve performance, like algorithmic improvements or better optimization or better architectures that can improve performance without having to increase the amount of compute they're using to train the language model.
Hey, Jason.
Oh.
Yeah, that was a good answer. Thanks. So I had a question. I thought it was really interesting, the part of the paper where you went into sort of potential reasons for these emergent properties. And at one point you showed that the cross entropy loss like tends to go down like more continuously compared to these other metrics like accuracy, that you see this sort of spike in performance at larger models. So I'm curious, like, basically it does seem like the model's learning something if you look at the cross entropy loss as you sort of increase the scale. So how much is it like due to like the metrics we're using that we see the spike? And then I'm just thinking like outside the domain of NLP, like do you also see similar sort of emergent properties and like do they follow similar patterns?
Yeah, great question. I think for maybe a small subset of tasks, like the metric can actually explain the sort of emergence where maybe the metric doesn't give partial credit. Or I guess the other thing is in the paper we have this plot where you can actually even see emergent spikes in the cross entropy loss for a specific task. And so maybe like if over like a certain corpus, the cross entropy loss improves like continuously, you can still get these spikes for certain types of tasks where the language model is suddenly able to do it. And yeah, I guess my best hypothesis for why emergence occurs is that as you increase the scale of the language model, you're able to spend parameters like learning edge, like tail end cases, and you don't have to like pick and choose between like, oh, do I have to learn this thing that's going to be very common in the distribution or very rare. I think that's one of the reasons why language models can like learn low resource languages just when they're bigger. So you know, like a large model, if you take a large model and a small model trained on like the same training data, the large model will be way better at speaking like or generating text in like a low resource language, because it doesn't have to like decide, oh, should I spend these parameters learning English or should I spend these parameters learning Swahili? And then I guess to your point about does emergence occur in other domains in AI? Definitely, there's been like some examples I can dig up, but I think the reason it's been so prominent in language is that like, well, I guess first, like we've done more scaling in language than I think in other domains. And also language has like sort of nice text-to-text format where you can like formulate any basically language task as text.
Thanks, Jason. I think we're running out of time. If there are more questions on Zoom or in the room, feel free to send them to us or maybe to Jason, and we can pass them along and get some answers. But maybe as one final question, Jason, I don't know whether you can answer this, but from the Zoom, what are you up to in your future endeavors at OpenAI? And if you can't answer that, maybe what types of research are you interested in seeing more generally from the community going forward?
Yeah, I think it's really exciting to see large language models being used out there in the world, and to have basically like, you know, a large portion of the internet pushing the limits of like what language models can do, and you know, incentivizing researchers to work hard on making them better. I think that's super exciting. And even within like the academic realm where you may not have access to, you know, a large language model, you know, I think there's a lot of great work that can be done to evaluate how language models work and to learn about why they have certain behaviors. And I think creating like benchmarks to sort of evaluate language models will be like a huge research direction that that will be very important, and I think everyone can contribute to.
Awesome. Thank you very much.
Great. Thanks for having me.